Okay, welcome to this second session of today. I would like to introduce Professor Inovia from Indonesia. She arrived last night late, but still she is here. So we thank you so much for coming and giving us this opportunity of the students to have who can listen you live, because you are already very popular among our local students, that you have a lot of work on metric dimension. Over to you, please. Thank you.
Thank you, everyone. This is my third time visit to Pakistan. Actually, I was in SMS, Lahore. I believe it was 2010. Yeah, and then I went to Islamabad for international workshop on discrete structure. Yeah, it was 2014, I believe. Yeah, so I was also there. So this is my third time, and I enjoyed my previous two visits. So I hope I can interact with all of you here and see more of Lahore. Okay, so I will be here until Saturday. I will give 4 lectures. So basically, I will talk about how to use matrix in graph labelings and also in Ramsey numbers. The first 3 parts will be about graph labelings. I will talk about different type of graph labelings. All right. So I should be there, right? Different type of graph labelings and also different type of matrices that can be used to construct labelings. And in the last session, I will talk about Ramsey numbers, yeah. In particular, multi-part Ramsey numbers, how we use metrics, in particular, Hadamard matrix to prove upper bounds for multi-part Ramsey numbers. Okay, so I'm from Indonesia. It's from a city called Bandung. It is about 120 kilometers from the capital, Jakarta. It's a small city in Indonesian term, yeah, but we have around 5 million people. So my university is Institut Teknologi Bandung, and I also am also from the Indonesian Center for Polarized Collaboration in Graphic. So this is the outline. Okay, so this is the outline of the course. I already mentioned before. The first one is this one. It's about matrices and magic labeling. So we will use, I think they are already familiar to you, magic squares, magic rectangles, and also fuzzy arrays. So we'll start with something which are familiar to you, and then we will move forward with several other matrices. So in the second course, I will talk about adjacency matrices, so the spectrum, so the eigenvalues of adjacency matrix that can be used to prove whether a labeling exists or not. And then we also will consider distance regular graphs, yeah, in particular strong irregular graphs and Harper cubes, and we will use their tri-diagonal matrix. Yeah, so if we have distance regular graph, we will have tri-diagonal matrix of those graphs, and we will use those also to consider distance magic labeling for those graphs. We will also consider a kind of matrix that we call completely separating system, and we will use this to construct anti-magic labelings or distance anti-magic labelings for subgraphs. And in the last course, I will talk about Hadamard matrices and how we use them to prove the upper bounds for multi-partite Ramsey numbers. So the first one will be based on something you maybe already familiar with. I will start with the beginning of magic labelings. Probably Andrea has talked about this last week, right? So magic labeling was having considered first introduced by Sedlacek in 1963. So basically, we label the edges of a graph with positive real numbers, such that if we consider any vertex, and we see all the edges incident to that vertex, it will give us, if we sum the labels, it will give us the same number. Okay, so you can see that here the codomain is a positive real number, and it Stewart in 1966 give more condition. So here he gave that the codomain has to be integers, consecutive integers. It can start from any integers, but actually for regular graphs, we can always start with one. But for non-regular, maybe we can start with other integers, right? The same properties, if we add the labels on the edges in each vertex, it has to sum up to the same cost. Okay, so this one also a very popular magic labeling, types of magic labeling. I think most of you have already know about it, maybe work with it. This was introduced by Alex Rosa, who also introduced the graceful labeling, another very popular, very famous graph labeling type. So this one is called H magic photo labeling. Although in their paper it is also called magic, but then it became very confusing because there are a lot of different types of labeling and all of them are called magic. So I think it was Wallis who gave this name, H magic photo labeling. So when we see the name, we know what kind of labeling it is. So total labeling means we label both vertices and edges. So here we have both vertices and edges being labeled. And by H magic, it means that we count the sum in each edge. So when we sum in each edge, it means there are only 3 labels in the edge, which is the label of the edge itself and the labels of the 2 answers, right? So we only add those 3 labels. You can see here, this one, right? And again, it has to sum up to the same cost. So this is what Anton Kotzig and Alex Rosa defined in the 70s. But I will not talk about this. I will talk about another type of graph labeling, which is called vertex magic photo labeling. But I will just show you some open problems in H magic photo labeling, which are very interesting, and it is still open until now. Probably it is a difficult question, but it should be a challenge for you. So here, you can think a little bit about it, and you can see that not all graphs are. So can you give me a small example which graphs are not H magic? Sorry. Isolated. Yeah. Okay. Yeah. All right. So that's okay. So, but for the case of 3, there is a conjecture by Rosa again that all 3s are H. So this is a very famous conjecture. It is still open. It's already more than 60 years old. And there is also another question by Paul Eros that was asked in Kalamazoo in 1996. He asked, what is the maximum number of edges for any H magic graph of order n? So if we have H magic graph of order n, how large, how dense the graph can be. So this was asked by in 1996, and this is the best, to my knowledge, the best result that we have until now. that the upper bound is order of n squared. Yeah, so basically it's 1 minus some epsilon, some small numbers, yeah, times n squared. And this was proved using probabilistic method in 2006 by all of people. Okay, so these are some big conjecture and big questions in the area of H-magic total labeling. And of course, there are also some other questions. There are always problems in mathematics. Okay, so now I will talk about vertex magic total labeling. So now instead of adding the labels in each edge, we add labels on vertices, right? Yeah. So here again, because this is total labeling, we again label the vertices and edges. Yeah. And the label has to be consecutive integers from 1, yeah, up to the number of vertices and edges. And we have a constant, yeah, when we add all the labels associated with a vertex. Yeah. So basically, what is the label associated with the vertex? Just the label of the vertex itself, plus all the labels of the edges with incident level, right? Okay, so they have to be positive. Yeah. Okay. So this is one example. This is just a complete graph minus 1h. Yeah. So if you see in this vertex, yeah, if you add the label of the vertex and all the incident edges, it will add up to 16, right? Yeah. If you do the same thing here, we will get the same number. Yeah. And also here and also. Yeah. So they are, so this graph is vertex magic. Yeah. But not all graphs are vertex magic. Yeah. We can consider if the graph has an isolated edge or vertex. Or two isolated vertices, sorry, not just an isolated vertex. So here is H, right? So why do you think this is not? So maybe there are another component here in the graph, but why do you think this is not vertex magic? Because yeah, we consider these two vertices, right? Yeah. We have to add the same labels. Yeah, for instance, they have labels A, B, and C. Yeah, in here, of course, we add A plus B. In here, we add B plus C. They have to be the same. In that case, A has to be the same with C, and we lose the condition of bijection. Yeah. Okay, and similarly, we also have to just two isolated vertices, right? Yeah. Those two vertices have to have the same labels. Okay, so now we want to use matrix to construct a labeling for a graph, particular graph. Yeah. So I think you are already familiar with magic square. Yeah. So what is a magic square? This is just an n by n matrix. Yeah. This is a magic square of order n. Yeah. And the entry is from 1 to until n squared. So we have different entries. Yeah. In each elements of the matrix. And we have that any row, any column, and then the main diagonal or the main back diagonal, yeah, they have to add to the same. Yeah. So I can give you some examples. This is of order 4, right? Yeah. So if you add here per column, per row, and also the diagonal and back diagonal, they all add to 34, yeah. Yeah. And also the same, this is of order 5, and this one is for order 6. Yeah. So let's see. And there are standard construction for magic square for all orders. Yeah. I think this is very well known. Yeah. Okay. I think, oh, sorry, there's a mistake here. This is supposed to be K33, yeah? So it's K33. Instead of K44, yeah, I will revise the slide, yeah? So use this following magic square of order 4, yeah, this is order 4 to vertex magically label, yeah? The complete bipartite graphs K33, yeah? How do you think we can do it? If we start with this, yeah? Is it K44? Yeah. Yeah. But we can do K33, right? If we so say K33, yeah. K44 is okay. Yeah, K44 is okay, but I will give a method, yeah, a procedure later on with one less. Yeah. So we will do K33. Yeah, it's also possible for K4. Okay. So how do you think we can do this? If I have this is the bipartisan sets, right, of K33, yeah. Which one, yeah, which column, which row that we can use to label the vertices in the first bipartisan. Or maybe we have to modify a little bit. Yeah, so yeah, of course, all the rows, all the columns will have the same yeah. So it will also have the same sum if I modify this magic square by reducing the elements with 1. Yeah, will it still be it's not a magic square, yeah, because we will start with 0, right? But then all the columns and all the rows will have the same sum, right? So if I take one less, yeah, of the elements there, so here's 0, 14, 7, and 5, and then 11, 13, 6, right, and so on. Yeah, you can fill in a square, right? So where do you think this number should go? This one in the first column. Huh? In the vertices of one of the sets, right? Yeah. Why is that? So if I put in 11, 13, and 6, yeah. And the others I put 14, 7, and 9. And of course I still have the edges, right? Yeah. And this is a total labeling, right? So we also have to label the edges. Which number should we label the edges? This one, for instance. With 5, yeah, with this one, yeah. So it's the element, yeah, you can say, yeah, this is between 11 and 14, yeah. So we can label the edge with 5, right? So is it true that the result will be vertex magic? Yeah. Why is that? Because in this vertex, for instance, yeah, what do we add? Here, yeah, this one, right? Plus here, right? All the entries here, right? And of course, they will give us and also this one, yeah, because this one is the label. Yeah. So of course, this will give us the same sum if we do for each vertex, right? Yeah, because they are the rows of modified, yeah, modified magic squares, right? Yeah. So in general, yeah, for KMM, So if we take a magic square of order n plus 1, okay, so this is supposed to be n plus 1, I'm sorry. The slides are a lot of mistakes here. Okay, so now each row and columns, yeah, will sums to this one, right? Yeah, you can try to see, yeah. Basically just add all the entries in the magic squares and then you divide with the number of rows. Okay, so now we construct another matrix, yeah, where we do the same thing, yeah. We take the elements one less than the original magic square, right? Right, and then we can also see that each row and columns will add up to this number, yeah. So it's the same with this one, but minus m plus 1, yeah, because we reduce everything by 1, yeah. So in each row we eliminate 1 m plus 1. Okay, so of course here the first one. Okay, the first one in this case, yeah, it is all because the entry of S11 is 1. Then when we reduce by 1, it becomes 0. And now it is easier. But it is not the case for general magic squares, right? For general magic squares, we can have 1 in any, right? So basically what we do is we permutate the rows and the columns, yeah? When we do that, permutate rows and columns, of course, we will not change the sum, right? Yeah. So in that case, we can have A11 as 0, yeah? And we proceed as we did here, right? Yeah. So we have another magic square, yeah. It is not really a magic square, but we start with 0, yeah. But then we can do a similar thing to what we have done before. We label the bipartisan sets with the elements of the elements of the first. Sorry, this is the first row, yeah, and the first column, yeah. So this is what was done by Jim McDougall, Mirka Miller, Slamin, and Wallis in 2002, when they proved that KMM has fantastic results. So they use reduced version of. Okay, so this one has to be M, yeah. So for the type. Okay, so that's for bipartite graphs with the same size, yeah. What about if we have different size? Yeah. Okay, so now assume we have M which is less than N, yeah. And this is a very typical technique in graph labeling when we want to show that the labeling, a particular labeling does not exist. Yeah, so basically we do counting. Yeah. So here, what we do is we sum the weights on one bipartisan set. Yeah. In here, yeah, we sum all the weights there. Yeah. So of course here, the first vertex has weight H. Yeah, everything has weight H. Sorry. So of course here we have the sum of all the weights will be M times H. Yeah. Okay. And if we consider the smallest, yeah, the smallest labels in here, yeah, what does it mean? It means that we eliminate the largest labels, yeah. So we don't put the largest labels here. We put the smallest label here, yeah. And here the sum, yeah, of the weights will be greater than this, right? Yeah. Okay. So yeah, we can do some calculation and then we can get the lower bound for H, right? And if we do similar thing with the other partition set, right? And we get an upper bound, yeah. But now we consider we label with largest labels, yeah. Because here KMN we have M plus N parentheses and then M ages, right? Yeah. So this is the largest label that we can have, yeah, and then we eliminate the smallest one, yeah. And here we get an upper bound for MH, yeah, and we can have the lower and upper bound here, and we can do some, just basic counting, and we can see that M will be larger than N minus 2 plus 2 over. Yeah.
Is it N and H? This under Y?
This is N, sorry. Yeah, this is supposed to be N. Yeah, because we, this is also supposed to be N. Yeah, so this is from Y1, Y2 until YN, and this is N. Okay. Yeah, but then we get the upper bound for H, yeah, and here we get this inequality, which means this value here is greater than N minus 1, right? Yeah, this value here is greater than N minus 1. Yeah, so we have M minus N supposed to be greater than, we can move it. So N minus M is less or equal than 1. Yeah. Yeah, because N is the larger value. Yeah. Okay. So N minus M is supposed to be less or equal to 1, sorry. Then in that case, if we have something larger, yeah, the labeling does not exist, yeah, because this condition has to be fulfilled, yeah. So here, if the difference between the size of the bipartisan sets is greater than 1, then we will have it. Yeah. Okay. So of course now, what about if we have K, M plus 1, right? And that's the next logical step. We cannot have more difference than this, yeah. And probably you can think about this, yeah, how to label this. This is a no results, yeah, it's already been proved, but I think it will be a nice exercise to you for using my matrix, yeah, to label graphs, right? Yeah, so construct fat magic labeling for this, yeah, and the known proof for this, we separated between M, even and odd. Yeah, we use different matrix, and the matrix that we use is what we call the quadratic array. Yeah. So what is a quadratic array? Yeah. Quadratic array is an M by N matrix. Yeah. M by N matrix. Yeah. Here, each row is a permutation of 1, 2 until N minus 1 from 0. Yeah. And every column has the same sign. Yeah. So again, what is this? This is an M by N matrix. Yeah. We have each row is a permutation, yeah, of from 0 up to N minus 1, and then every column has the same sign. Yeah. So this is easy, right? For 2 by N. Yeah. This is 2 by N. Yeah. You just go this direction, yeah, going up, and then on the second row you go down, and of course if you add in every column, yeah, it will add up to N minus 1, right? Yeah. And for 3 by N, this is 3 by N, yeah, what you do is, this is similar, right? Yeah. But then you change a bit here, yeah, so you go from 2 R to 0 here, and this is all the even number, yeah, and here you change with the odd number, right? Yeah. And then here, so if you see here, the sum will be what? 3R, right? Yeah. So in order for this column to be 3R, this has to be 1, yeah, and so on. Yeah, it goes up until R minus 1, and then the R we move here. Yeah, so you can see that the sum will also be 3R everywhere. Yeah. So based on this easy construction, yeah, for 2 times N and 3 times N, of course you can construct for all sides, right? Is it correct? You just put together, right? Yeah. So for instance, if you want to have M by N, where M is even, you just stack together all the tools, right? Yeah. And then if you want to have odd, you put this and some even. Yeah.
But it must have odd length, right?
Sorry.
It has odd number of columns together.
Here number of column is, here is should be on, yeah. Yeah, because here we have, let me see. This is to R, yeah, this is, yeah, number of column is on. But here it can be, yeah. But, okay, so if we have M times M is on, and M is on, yeah, then we can do this one, and then we add like the, yeah, this part here, yeah, okay, right? But if we have one of them is even, then we just use, yeah, okay, so we get everything. Is that right? Yeah, I don't know. Okay, so yeah, this is a very well-known result, yeah, from, it was first mentioned by Anton Pasik, but probably it is already there somewhere in China, probably like hundreds of years ago. I don't know. So here, and by using this, yeah, this is 2003 result by Gray, McDougall, Simpson, and Wallace. They can prove that if M minus N is the difference between M and minus 1 is less than 1, then KMN has a vertex magic value. Right? Okay, so you can think a little bit about this, yeah. Think about the quadratic array and then how to use them, yeah. Of course, you have to change, yeah, because here you have repetition of labels, yeah. You have to do something, yeah, to use it to label KM. Okay. All right. So these are some conjecture, yeah. There's only one conjecture actually, which I find very interesting. Yeah, there are a lot of open problems still in vertex magic photo labeling, but I just want to mention one. Yeah, so this is by McDougall. He said that all regular graphs other than K2 and 2 times K3, yeah, are vertex. Yeah, this is a difficult conjecture. I believe it is a difficult conjecture. Yeah, some partial results have been proved. Yeah, so yeah, Jim McDougall, Gray, and Wallace proved that all complete graphs are vertex magic. Yeah. Actually, the proofs are separated into several papers. Yeah, so they consider cases like even, and I forgot, but like 0 mod something. Yeah. So there are several papers for proving just complete graphs are vertex magic. Yeah. But I think because of they can label, yeah, all complete graphs vertex magically, they believe that it also happens. Yeah, it also happens. It is also will happen for other regulars. Yeah, so that's they believe. So this is big breakthrough by Gray in 2007. Yeah, he proved that almost all regular graphs of odd order are vertex magic. Yeah, so he couldn't label like just small. Yeah, it's still infinite set, but yeah, so almost all regular graphs of odd order has been proved to be vertex magic. Yeah, and what about the even orders? Yeah, several cases of large classes of regular graphs of even order, and also which include some Hamiltonian graphs are oriented to be vertex magic. But this is still open. So if you like challenge, yeah, you can try to think about it. Yeah, maybe consider some classes of graph which have not been considered by Gray in his 2 papers. I think this one is, if you want to look it up, this is in CIMPA discrete math. This one is in discrete math type. Yeah, but if you just type Gray and McDougall, and you can see all of this. Okay, so now we will move to another type of labeling. Yeah, so I mainly work in this kind of labeling. Yeah, so distance-based labeling, not really the H magic total or vertex magic total. So the difference with the previous labeling is now we consider only vertex labeling, yeah? In the sense that we only label vertices. Yeah? We only label vertices. And how do we count the weight? Yeah, we count in each vertex. Yeah, we add the labels of vertices adjacent, yeah, adjacent to that vertex. Yeah, so because we only label the vertices, yeah, only vertices have label. In each vertex, we add the label of vertices adjacent to that particular. Yeah, so this is what we add. Yeah, this is the three smallest example. Yeah, we have the three here. Yeah, if I add this, the neighbor of one is 3. Yeah, the neighbor of 2 is also 3. The neighbor is 3 is 1 and 2. If we'll add up to the same number. And also in here you can do the same thing. Yeah, add up the labels of each adjacent, all adjacent vertices of a particular. Yeah, so we sum the labels of the neighbors. Yeah. Okay, so this was defined by Bill Pratt in 1994, but actually he used a different name. Yeah, it is called Sigma labeling at the time, and it was not published. This was part of his dissertation. So basically, people don't really know about it. Yeah, so we thought we defined it in 2003, but actually it's not. Yeah, it's already defined in 1994. Yeah, but now if we go back to the complete multipartite graphs, not to the magic square of order 4, yeah. What kind of complete multipartite graphs you think that we can label? Yeah, distance with distance matrix labeling by using this. By using this. So yeah, I repeat again. In magic square, we have the same sum in each. Now it's gone. In each column and each row, right? So if we want to label complete multipartite graphs, yeah, what kind of complete multipartite graphs we can label one? Okay, yeah, that's true. Yeah, K4444. Yeah, so we have 4 partitions. That's each of them has 4 vertices, right? Yeah. So I guess I can use either the column or the rows, right? For instance, I use the column here. In here, 1, 12, 14, 7. Yeah. And I use the other column, yeah, the element of the other columns here and here. Yeah. And you can see in so the vertices in the same partner set will sum up to the same number, right? Because they are columns of magic, right? Yeah. And for instance, if you consider this vertex, yeah, which one will you add? The label of the neighbors. Yeah? Which one are they? Yeah, 3 times. Yeah, this sum. Yeah. So we can have a distance magic labeling now. Yeah, by using this magic square. Right? Yeah. And of course, we can use larger, what is that? Yeah, larger squares, right? And actually, we can generalize by using magic rectangles. Yeah. So what is a magic rectangles? Yeah. So this is an m by n magic rectangles. Yeah. So again, this is not n squared. It's supposed to be n times n. Yeah. And here, the row sums equal, and also the column sums are equal. Yeah. Okay. So of course, in m by n magic, m by n matrix, we will not have diagonal. Yeah. So we just exclude the diagonals. Yeah. So what we want is just the sum of the column and the rows to be the same. Yeah. Okay. So by using this, yeah, we can now label what kind of graphs, yeah. So multipartite graphs, yeah, with multipartite graphs with m-partite sets, yeah. Each have size n, yeah. We can use this magic rectangle, right? Yeah, the same way we do the m times m by using magic squares. Okay. All right. And yeah. So the construction, yeah, we can use like a known magic squares, and by using the known magic rectangles, yeah, we can have these conditions, yeah. So this can only be done when n is even or n and m are odd. Yeah. So there is some counting argument, yeah, to give us this condition. Yeah. So these are some examples. Yeah. So this is the number of 1, 2, 3, 4, 5. Yeah, each partite set contains of 6 vertices, right? There are 5 sets, right? Yeah, so this is the notation that we use. And you just use the element in of one column in a magic rectangle. Yeah, and we can do this is for all odd. This is if one of them is even. Yeah. Okay. All right. So this is for complete multipartite graphs with the same size. Yeah. But now, what about for different size? Yeah. For different size. Yeah. And then it becomes complicated, yeah, because we cannot use magic square, magic rectangle. We cannot do it, yeah, because yeah, the number of vertices in each set will be different. Yeah, can be different. Yeah. So this is our conjecture in 2003. Yeah. Where we conjecture that the distance magic labeling exists, yeah, given, and this is the characterization, yeah. So these are the conditions, yeah. So first one, the second set has to have must have at least 2 vertices, yeah. It cannot have one, yeah. Maybe you can deduce the reason why you can have it. And this one is basically just to count the magic constant, yeah. This is basically to count the magic constant. And this is a condition where we basically want to have one set to add up to the same sum, yeah. So this is the condition, yeah. I will show you later on, yeah. But yeah, what I want to show you that this is not yet solved. Yeah, this is still open, the conjecture. Yeah, it is true for bipartite and tripartite. Yeah, and the latest evidence for the truth of the conjecture is for complete multipartite graphs with 4 sets. Yeah, this was proved in 2016, and then it for the rest of the values of p. Yeah. So I think I will give you an example, yeah, that probably will give you an idea why is it so difficult to write, yeah, to write the proof, yeah. The idea probably not very difficult, but then writing is a different. So say we have maybe I have 18 vertices, yeah. Yeah. So if we start with 7 and 11, so 7 and yeah, because this is going up, the number of vertices 1, 2, 3, 4, 5, 7, and 11 here. 4, 5, 6, 7. Yeah. Correct. 4, 1, 2.
Like what?
I need more. Okay. All right. So here, of course, yeah, if you want this graph to be labeled distance magically, yeah, all the parallel sets, yeah, in this case, the two parallel sets has to have the same sum, right? Yeah. Why? Because of course, like here, yeah, the neighbors of this vertex is only this one, right? All the vertices in here, and the neighbor from this vertex here is all the vertices in here, yeah. So both of them has to have the same, yeah, all the vertices, yeah. So basically, if we add all the labels, yeah, from 1 to up to here 18 in this case, yeah, they should be divisible by 2, right? Which is the magic constant, right? Okay. Yeah. So what is this? This is just 18 times 19 over 4, right? Yeah. So you can see how we get the second condition, right? Yeah. So basically this one, n plus n plus 1 over 2, yeah, is just the sum of all the labels in the graph, yeah. And of course, they have to be divisible by the number of, yeah, to get the magic constant. Yeah. Okay. All right. So here, what is the? So is this divisible by 4? Wait. No. No. Yeah. So we take wrong division for 18 vertices here. So what should it be? Instead of what is that I used before, 7 and 11, yeah. So what should we use? 8 and 10. That's one obvious example, right? So 8 and 10, we will fulfill the second condition, right? Is it correct? Yeah.
Doesn't depend on the size.
No, this is just 2. This is just by 1. This is just by 1. Okay, right? 8 and 10. Will it work? No. Or 18 will not work, yeah, in general, yeah, 18 will not. So what do you think will work? 16? 16 will work, yeah, okay. So if we have 16, so I reduce 1 and 1, yeah. Now we can try to label, yeah. But of course there is a third condition here, yeah, where we have to make sure that so here is 16, here we have 16 times 17 over 4. This is just 4 times 17, which is 16, yeah. Okay. All right. So we have to make sure that if we label the vertices in here, it can be summed up to 68, right? So if we start with the largest label, yeah, the largest label is 16, yeah, 15, 14, yeah, is this already past 68 or not? No. 13, no. 12, yeah. What is this? 70. Okay, so in this case, we skip this label, yeah, right? So you can see that the third condition will ensure us that even though the number of vertices in the first set is small, we can still achieve the sum, the magic sum that we want, right? Otherwise, if you try to reduce this number of vertices, for instance, only 3 here, and then we have 13 here, of course we cannot achieve 68, right? So that's why we have the condition. So that's just to ensure that we will have it in each. Okay, right? So of course you can continue, you can reduce, you can use smaller labels, and if you get 68 here, of course you will get 68 on the other side. So that's how we do it. The idea is not difficult, I think. So basically, given this, we can always do this. But then to write it, we can write it for up to 3 part-type graphs. So basically, what we have to ensure in the proof that we can always find the adequate labels, to get into the desired sum. So basically, we have largest labels, and then we have some gaps, and then we have smallest labels. And we have to show that it is always possible to achieve the sum, by those constructions. But it is not easy to generalize. It has been only up to 3, 4.
Still, preference more diverse. Whole terms on this magnetic constant. Is some first 16 versus then 30 scales and criteria.
Can you repeat the question?
What if you have here to find this magic constant?
The criteria to find the magic constant is basically just adding all the labels, and then we divide with the we sum of the labels, in the graphs, and then we divide with the number of finite. So that's the sum for one set. In bipartite graphs, it will be the magic constant. But for instance, if we use 3 part-type graphs, of course, if we have all of these have the same number, as we have the same sum, right? And for instance, if we take this vertex here, the adjacent vertices will be the vertices in the other 2. So the constant will be 2 times. But still, each of the set has to have the same sum. We divide the sum of all the labels by 3, and then the magic constant will be 2. If we have here P partition, so you can see in here, right? So n times n plus 1 over 2, which actually should be congruent to 0 mod P. So that's the magic. Okay, but again, how to construct the labeling is still a big question, and we have done it up to 3, and then Peter Kotlar proved it 4. So this is just a flavor of what I will talk about in the next 3 lectures. So basically how we use matrices, for labelings, and then at the end for transient. Okay, so use one combinatorial structure to construct other combinatorial structures. Okay, all right. I think that's all for today. I will still have 3 more lectures, and hopefully you will learn something from it. I will talk also about open problems and conjectures for distance magic labeling. So I didn't mention anything in here except for the multipartite, but there are still many. Thank you.
Any questions? You can ask them.
So this is the building in our campus, yeah. So I hope you all can visit us someday. Yeah, so this is what we call so we have a twin main hall, yeah, west and east. This is the west one. Yeah, you've been there.
So, in the Lenovo group in Indonesia is too much working on magic sphere and magic labelings. If someone is interested on this topic, you can just search out this group of Indonesia. Lot of working is there and still too many open problems about magic and anti-magic labelings. So if someone is interested, just contact with this group in Indonesia. There are too much open problems still. So that's we have 5 minutes break, and after 5 minutes break, we will start with the next session.
Okay, thank you.